So let's now talk about capacitors with dielectrics and let's see if we can understand how they work. So a dielectric is an insulating piece of material and it's placed between the plates of a capacitor. If you're trying to imagine what this might look like, picture two sheets of aluminum foil separated by a thin piece of plastic. It looks something like that. There are three functions of a dielectric. It keeps the metal plates of a capacitor from touching each other. That would cause a short in your circuit. It increases the maximum possible potential between the plates, and that's an experimentally observed result. And it also increases the capacitance compared to if we had the same capacitor, just separated by air. Okay, let's set it up and see what we get. So let's first think about what if we have a capacitor with just air between the plates or a vacuum. That's basically the same thing. We would connect our capacitor plates to a battery that would have potential delta VO. So our first step would be to connect the capacitor to a battery or source of potential, and that battery has potential delta VO. And here in my expressions, I'm going to use O to refer to the air space or the vacuum space, so when there's nothing between the plates. What happens when we hook up that battery to that capacitor is that the plates are going to get charged up. One plate will have positive charge and one plate will have negative charge. This separation of charge results in an electric field between the plates. Okay, I'm going to draw that electric field next. It's a little bit hard to draw in 3D, but I will do my very best. Okay, hopefully you're getting the idea. There's an electric field going from the positive plate to the negative plate. This electric field is the electric field of a capacitor with just air between the plates, so I'm going to call that field E with a 0 on it. When we have our fully charged capacitor, the total charge on each plate is going to be plus QO on one plate and minus QO on the other plate. So when it's fully charged, we'll say that the charge on each plate is either plus Q on the positive plate or minus QO on the negative plate. Once it's fully charged, it's going to have the same potential as the battery. So the potential across the plates of the capacitor will be delta VO, exactly the same as the battery. So if we wanted to, we could calculate the capacitance of this capacitor. It would have a capacitance, which is the charge, QO, divided by delta VO. So far we haven't done anything new. We said the charge on the plate is QO, the potential across the plates is delta VO, the capacitance is the charge divided by the potential. And we've written everything with an O just to indicate we're talking about a capacitor with air between the plates or vacuum between the plates. We could also write down the charge density if we wish, and why don't we put that in our list? So our charge density, sigma O, would be the charge QO divided by the area of the plates. Okay, when we were doing an equation here for C, if we wanted to use the equation for C with epsilon in it, of course we would use epsilon naught. Okay, our next step, leading us to a capacitor with a dielectric between the plates. First, we'll talk about what we'd physically do. The first thing we would physically do is remove the battery. So we'd unplug the wires to the battery. So let's write that down in our step. We remove the battery. So let's say it was attached by two wires going to the two terminals. We just take those wires right off. So that's the first thing we do. The second thing we do is we put that dielectric between the plates. Say it's a piece of plastic. We just slide the plastic between the plates. So our next step is we will insert the dielectric. So that's a piece of insulating material. Okay, so now what happens after we remove the battery and we insert the dielectric? The first thing that's important is we've taken apart the circuit. It's not connected to wires anymore. That means there can't be any more flow of charge. So let's write down that note. Charge cannot flow. Because we've taken away the wires and the battery. Let's see, what else do we have? So if the charge can't flow, what's the implication of that? Well, if the charge can't change, it means the charge is unchanged. So our new capacitor with this dielectric, this hunk of whatever between the plates, is the same as the old charge because the charge is not able to flow. So let's write that down in a note. Charge is the same. So the new charge, we might call that Q, is exactly the same as the old charge because the charge was not able to move around. Okay, if the charge is the same and we haven't changed the area of the plates, then the charge density is also the same. So plus or minus sigma is equal to plus or minus sigma naught. No change in charge density because there's no change in charge. The potential between the plates, now that is different, and we see that experimentally. If we set this up, we pop in a voltmeter, we would see a difference. So let's put in that note. Potential between the plates changes. So potential between plates changes. Put an exclamation point because that's kind of exciting. So the new potential is delta V C of the capacitor. So this means the potential difference of the capacitor with the dielectric inserted. This is new, this is different, and we see that it is smaller than the original potential difference, delta V O. And that is an experimental result, EXPT, to tell us that experiments show us that that's true. Now that we've written down the charge on our capacitor with a dielectric and the potential of our capacitor with a dielectric, let's use that to find the capacitance of the capacitor with the dielectric. So we know capacitance C is charge divided by potential. The charge on the capacitor plates with and without the dielectric is exactly the same. It's QO. The potential between the plates with the dielectric, we call that delta VC. All right, so let's do something with this QO. Well, we know from our capacitor without the dielectric, QO is equal to the original capacitance times the original potential. Let's fill that bit in. So QO is equal to CO times delta VO. That's all divided by delta VC. Now I'm just going to haul my CO outside. And let's look at this for a moment. Delta VO divided by delta VC. So the potential between the plates of a capacitor with just air divided by the potential between the plates of a capacitor with a dielectric. This term has got to be greater than 1 because delta VC is smaller than delta VO. So this bit right here is greater than 1. And we know that that's true from experiments. So the result, the conclusion, is that our new capacitance is bigger than our original capacitance. When you put a dielectric in, we increase the capacitance of a capacitor. So why is that important? Well, we know capacitance is related to energy. If we can increase the capacitance, we can store more energy in that capacitor and in our circuit. So let's try and get down to the nitty-gritty of what's happening. Why does our capacitance increase? What makes it change? So let's think about this dielectric for a moment. All we've said so far is that this dielectric is made of insulating material. And the dielectric, like everything, it's full of molecules. So what happens to that dielectric when it's in between the plates of this capacitor? Well, when we had our capacitor without the dielectric, the separation of charges created an electric field. We still have that same deal with the dielectric. We still have two plates. They're still separated by distance. There's still that electric field created by the plates of the capacitor. So we can still draw that field. It still applies. It's even harder to draw 3D with this stuff in the middle, but hopefully you can kind of see it anyway. So this electric field is still there. This EO between the plates still exists. It's made by the plates. Okay, what about the dielectric? So now we have this material and it's sitting in an electric field. The dielectric is full of molecules. Molecules are charged, so the individual molecules of the dielectric, they're going to tend to flip and line up with the field because those charged ends are going to feel electric forces. So they're going to flip so that the negative end is closer to the positive plate and the positive end is closer to the negative plate. So that's what's going to happen to the molecules in the dielectric. They're going to line up or polarize. You might remember this from before. So the molecules all get polarized. Okay, let's think about what that means. What this means is that on this end of the dielectric, where all of the negatives have flipped to be closer to the positive plate, this end of the dielectric is going to tend to have a net negative side. So right here, there will be a net negative. On the other end, where all the positives have flipped to get closer to the negative plate, that's going to be a net positive side. Let's think about what that means. We have one side of our dielectric is positive, one side is negative. That's a separation of charge. This is going to induce an electric field. So overall, this will create a new electric field induced by the lining up of those molecules. We might call that EI for E induced. Okay, so EI is an electric field induced in the dielectric by the motion of those molecules, getting them to flip over in the material. So now what we have is two electric fields. We have one created by the plates, we have one created inside the dielectrics. Let's see what that gives us. Let's talk some more about these electric fields and see what they tell us. First thing I'm going to do is move to a two-dimensional diagram. This 3D stuff is killing me. So for my edge-on view, I have my two plates, positive and negative. First, let's consider the case with no dielectric between the plates. That's when we get an electric field that we labeled EO. I'll draw that one again. Electric field points to the left here. When we place a dielectric between the plates, I'll just draw that in. What happens when we place that dielectric is it makes all the molecules flip and line up, and it induces a new electric field in the dielectric. And that one we called EI for an induced field. Then the total electric field between the plates of our capacitor with a dielectric in place is going to be the vector sum of those two electric fields. So our new total electric field between the two plates is our vector sum of EO plus EI. What about the magnitude of that field? Well, let's take our coordinate system so that positive x points in the direction of our original electric field. So the magnitude of our new total field between the plates of the capacitor with a dielectric in there is going to be EO. That one points in the direction of positive x because it's positive. Subtract EI, and EI is negative because it points in the direction of negative x. What we see here is that EO is greater than E. So when we put in the dielectric, the field is a little bit smaller between the plates under the conditions we talked about on the previous slide. Okay, I'm going to define a new quantity that I'm going to give a symbol of the Greek letter kappa. That's like a K, but a little bit curlier. And kappa is going to be the ratio of those two fields, EO divided by E. The field without the dielectric divided by the total field with the dielectric. We know that EO is greater than E. That tells us, so because EO is greater than E, that tells us that kappa must be bigger than 1. This kappa value we call the dielectric constant. It depends on what the dielectric is like. Dielectric constant. And the dielectric constant is an indicator on how the molecules of a dielectric are able to polarize or line up when they're placed in an external field. It depends on the type of material, and all materials have different values of kappa. So where else can we use kappa? So for the first thing, let's talk about the electric fields. Let's rearrange this equation and let's solve it for E. So what we get when we do that is E is equal to EO divided by kappa. EO is the electric field between the plates of a capacitor with no dielectric between the plates. We remember from Gauss's law that electric field is equal to the charge density divided by epsilon naught. So let's just fill that bit in. So now in our denominator, we see that we have epsilon naught times K. We can write that as epsilon. So sigma naught divided by epsilon. Epsilon, which we just said was epsilon naught times kappa, the dielectric constant, this is called the permittivity of the dielectric. Okay, what does that mean? Well, electric field in a capacitor with no dielectric, we use epsilon naught because it talks about how the field goes through space or a vacuum. If it does have a dielectric, we use epsilon, and that describes how electric field goes through a material. Okay, so that's when we use epsilon. Epsilon naught is if we have a vacuum. Epsilon naught is when we have a material. Okay, let's see if we can link it to capacitance. I think I might spill on to the next slide though. To get to capacitance, let's first think about potential. So the potential between the plates of a capacitor with a dielectric between the plates is the total electric field between the plates times the plate separation D. The electric field between the plates, the new total electric field, is EO divided by kappa. That's our expression we had right here, and we're multiplying that by D. And then EO times D, you can recognize this as the potential difference between the plates of a capacitor with no dielectric. That's our delta VO. So this gives us a relationship for the potential between the plates of a capacitor with and without a dielectric. Delta V with the dielectric is delta V without the dielectric divided by the dielectric constant kappa. This matches our experimental observations that the potential drops when we place a dielectric between the plates. Okay, so that talks about potential. We said we were going to talk about capacitance, so let's do that next. So our new capacitance between the plates of a capacitor with a dielectric, is the charge between the plates. Remember, the charge didn't change because we disconnected the battery, so it was always QO, divided by the potential between the plates. Okay, so this is with the dielectric. This is our new capacitance with the dielectric in place. So let's put in for delta VC, that delta VC is delta VO, the original potential, divided by the dielectric constant kappa. That's in the denominator of the denominator, so our kappa comes up top. Okay, QO over delta VO, that's the original capacitance. So that's kappa times CO. So our result here, when we place a dielectric between the plates, our new capacitance is the dielectric constant times the capacitance without the dielectric. So when we place a dielectric between the plates of a capacitor, it increases the capacitance because kappa is bigger than 1. So overall, kappa, our dielectric constant, it tells us what happens with the electric field, the electric potential, and the capacitance when we have a dielectric in place. So let's throw back now to an example we did previously. We had a capacitance of 1 farad, plate separation of 1 millimeter. We assumed there was no dielectric, and we found the area of the plates. You may recall that when we did that, we found that the plates had an area of 10.6 kilometers by 10.6 kilometers, totally unreasonable. So what would happen if we placed a dielectric between those plates, say strontium titanate, which had a dielectric constant of 300. This is just something you can look up in a book. Then what would the area of those plates be? So if we had a capacitor with this dielectric, what would be the area of those plates? So let's write down the equation for capacitance of a capacitor with a dielectric between the plates. It's the dielectric constant times the capacitance without the dielectric. So that would be kappa times epsilon naught times A over D. We're trying to find our area, so let's solve for A. A is equal to D times C divided by kappa times epsilon naught. Let's make sure we know what our numbers are. D is the plate separation, 1 millimeter. C is our capacitance, 1 farad. What's next? Kappa is our dielectric constant, that's 300. Epsilon naught is the permittivity of free space, 8.85 times 10 to the minus 12 farads per meter. When we run that through the calculator, what we get for our area is 3.77 times 10 to the 5 meters squared. If you thought about what those plates would look like if they were a square, that'd be 614 meters by 614 meters. In my opinion, that is still too big. That kind of goes to show that a capacitance of 1 farad is still too big. It's an unreasonable capacitance. There are things we can do to change this. If you wanted a smaller area, you might push the plates closer together. You get a smaller value of D. So you'd get your layer of dielectric that was even thinner, and then you might be able to roll up those plates just to make it even smaller with a big area. This feels like a good time to mention a FET simulation about capacitors. If you Google FET, PHET, and capacitance, it should take you to this simulation. What we can do is we can hook up a simple circuit, a battery to a capacitor, and we can check it out. So we turn on the battery, turn up the voltage, connect the capacitor, it charges up the plates, and then we can disconnect our battery so the charge can't change. We can see what happens when we change the distance between the plates. And we can also see what happens when we change the area of the plates. We can look at what happens to the capacitance for both of those things. So this simulation might be a way for you to get a handle on how to work with capacitors a little bit.